Hey all, it's Dr. B. This is just a lecture for Chapter 13, Energy and Matter in the Atmosphere. Let's get right to it. Obviously, the big statement or point that I've been covering probably the whole semester is the difference between these two words. And remember, weather is like what it's outside today, or this week, or this month, or potentially even this year if it's a rainy year. But then climate, of course, is a long period of time. Florida generally is very hot and humid. Siberia is usually very dry and super cold, like that. That would be the climate. So this is one thing a lot of students sometimes don't realize. A lot of them just think that, oh, the atmosphere, it's all oxygen because that's what we breathe. That's not right. Most of it is nitrogen. By far, and you can see that oxygen is about 20%. Then there's all kinds of other little things around there, but just generically speaking, understand that nitrogen is the vast majority of gas, and then oxygen is a second place with around 20%. I want to address this graph that's in the book. On one end, I saw their intent, and the purpose is to show you that the amount of CO2 in the air is increasing and has since the 1960s. But there's also something, in my opinion, very misleading about this graph. And that's because the y-axis starts at 320 parts per million and not at zero. So understand that the amount of the increase of CO2 is not as drastic as this. But what I do like about it is that it zigzags. And you can see during a year, and I'll talk about this in class, that the amount of carbon dioxide in the winter is higher than it is in the summer because there's no leaves in the winter, or not as many. Pine trees, actually, those little needles are actually leaves. But all the deciduous trees have dropped their leaves, therefore decreasing the amount of leaves to suck in the CO2 from the atmosphere. So one of the aspects of the atmosphere is something called ozone, and you may have heard about it with the ozone layer. And I was a kid, it was a big issue because there was a hole in it. And there still is one. It's not as bad as it was. But basically, it's O3. And it serves a purpose where it absorbs harmful UV radiation. So obviously we had a fear when we had a gigantic hole in the ozone layer that ultraviolet radiation from the sun would hit people and make them, have way more higher radiation. A lot of the depletion was caused by CFCs, which is an ingredient, a propulsive ingredient they used to be in things like hairspray and spray paint, things that pushed out a liquid from an aerosol can. It's since been banned, and there's a couple other things that have been banned as well. This kind of gives you a generic view of how we were able to determine the hole in the ozone and what's happened to it. It's starting to get smaller, which is kind of nice. I like this graph in terms of other aspects of the atmosphere, like pressure. And you probably know this from, if any of you have taken a plane. But you'll notice that the pressure goes up as the altitude decreases, meaning that, and that would make sense, that literally the weight of, in essence, all of that air, and air is not weightless, it's very thick, it increases. And so you can see here that it would make sense why airplanes fly right around 30 to 40,000 feet, which is right around here. They do that partially because there's less traffic, but they also do it because they can save a hell of a lot of gas because there's not as much air to push against the airplane. So they can go a lot faster. It's also super cold out. I don't know if you realize this, but when you're in an airplane, next time if you happen to go on like an international flight, and they tell you the information outside, it can typically be minus 20 to minus 30 degrees, maybe even a little colder when you're flying at 40,000 feet, which is kind of crazy. For the exam, you'll need to know the different levels of the atmosphere. The troposphere is the bottom layer, and that kind of makes sense, and I'm just going to move down to some of the other ones here. We have the stratosphere, which is the next, and then the mesosphere. And then from that point, we have the thermosphere. And we're kind of see where we're going up from that in essence. And you can see that this is a really good kind of graph that has to do with literally temperature changes in terms of also height. And just to give you an idea that even Mount Everest, the highest mountain, barely touches the top of the troposphere. So now that we covered the atmosphere, let's talk a little bit more about the Earth and the Sun. And I had covered this to a degree, but again, as a rewind, that the Earth rotates on its axis and it revolves around the Sun. So rotate would be if you take like a basketball in your finger and spin it. That's rotating. And the seasons are because of the angle of the Earth. The fact that it's tilted X degrees gives us what's basically seasonality. Um, so let me just spend a little bit more time on some of the pictures that would help with that idea. And this is a great picture. So the question again is how many degrees? It's about 23 and a half. And you can see here that this magnetic north and south. And so that's why the globe, if any of you guys know what a globe is from when you're little kids, that's why it's tilted like that. It's kind of representing that idea. So, a question you might ask is for the northern hemisphere, which is us, is this more wintertime or more summertime? And the answer is it's more wintertime because you can see we're tilted away from the sun. So the angle of refraction is different than it would be if we were in the southern hemisphere, more directly in the path of the sun and spending more time in the sun because we're tilted towards it. And this is just another picture that shows that idea. Like if we're just spinning around this way, right? You can see us kind of, there we are, rotating around. We're in the sun a lot more. And as we continue to notice, by the way, we stay at this axis. We're still at the axis of this angle. But now once we revolve around the Earth, now it's December. Now we're revolving whereby more of us is away from the sun, and that's what causes those seasons. And while you're halfway between the extreme of June 21 and December 21, that's when you have your equinoxes like spring and fall. Another thing you'll obviously need to know is how heat can be transferred: conduction, convection, and radiation. And heat basically, it's an interesting term, what really heat is. It's a very interesting thing. It's always transferred from warmer to colder, but like, what is it? It's basically energy. It's a change in energy. And things that move more are what you would probably consider hotter, like in the sense of if you light a fire and you stand near it, you feel warm. What that really is just the molecules of the air that have gained energy from the fire. And as you move farther and farther away from the fire, the temperature decreases. So these three terms, conduction, convection, and radiation, are words you're obviously going to need to know. So just to give you this picture as an example, you have radiation, which is basically the radiating of energy. And this is absorbed by this pot. And what it's doing is it's making the molecules of water move faster. And as they move faster, it creates friction and more energy, and that's what heats it up. But the interesting thing about it is the convection part, where basically the heat goes from areas where there's more of itself to where there's less of itself. And that idea is basically convection. And it's because the heat itself represents the molecules that can move faster than the cold things where those molecules can't move as faster. So in essence, the replacement. And you can see here the idea that you would have this super hot molecules that would rise to the top, right? And then all of a sudden they get to the top, they get cooler, and they start to fall back down, and then they get hot again from their radiation. And then of course the conduction would be the relationship of that energy being transferred to a physical body such as a metal or whatnot. So you can go ahead and work on the radiation part just to give you a generic idea of that. But in essence, what happens, how does that involve solar radiation? It involves the idea of direct radiation that's absorbed. Some of it bounces back into space. And we talked about that with the fear of the melting of the glaciers, is that a lot of that radiation would have reflected off the surface of the Earth and back into space. But now that there's not as much ice, that water, or I should say that radiation, is getting absorbed by land, and more specifically the ocean, which holds on to that radiation, unfortunately, very well, therefore perpetuating the heating of the Earth and the ocean itself. Just as another reiteration of that, I kind of like this example here where you can see where we have conduction, which is an energy transfer via direct contact. And that is conduction. And there are obviously some things that can conduct heat really well, like a lot of metals, but there's things that can't conduct heat very well, like wood, and that's why, or plastic, and that's why a lot of handles of pots have a wooden or plastic to them, because they do not conduct energy very well. Then again, you have the idea of convection, where you have your heat transfer by flow. where the hot moves up to the cold, and slowly then as it becomes cold, falls back down and becomes reheated, etc. And then, of course, the radiation is the energy transfer of EMF, or electromagnetic fields. And those three together worked on something called the greenhouse effect, which I'm not going to cover in this video. I will cover that in class. So I hope you enjoyed this overview of Chapter 13. Again, I will cover the greenhouse effect in class for it, but at least that gives you a pretty good basis of the major aspects of Chapter 13 that you need to know for the exam. See you later.